afternoon, everyone, and welcome back to the Brainy Boomer Lecture Series. We're also very happy that you've joined us today. We would like to begin by acknowledging that the McGill University Research Center for Studies in Aging is located and our work is done on unceded Indigenous lands. The Kanien'kehá:ka Nation is recognized as the custodians of the lands and waters on which we gather today. Tiohtià:ke, commonly known as Montreal, is historically known as a gathering place for many Indigenous peoples. Today, it is home to a diverse population of Indigenous and other peoples. We respect the continued connections with the past, present, and future in our ongoing relationships with Indigenous and other peoples we serve who live within the Montreal community. In 2007, the McGill University Research Center for Studies in Aging, or the MCSH Education Committee, started the Brainy Boomer Lecture Series in order to suggest practical steps to both improve and maintain brain health, as well as to promote healthy lifestyle choices amongst the most populous generation in history. The MCSH Education Committee, which was founded in 1996, has three main objectives: identifying education needs of healthcare providers, seniors, caregivers, and the public, and to develop responses to meet some of these needs, to enhance the positive image of the aging process by addressing stereotypes and myths about aging, and finally, the dissemination of research on aging. Our guest today is Dr. José Moret, who is a full professor of medicine at McGill University. He holds an MD degree from the University of Montreal and completed a specialty in internal medicine and geriatrics at McGill University. He went on to complete a 3-year research fellowship in nutrition and metabolism at the McGill Nutrition Center. He is senior scientist at the Research Institute of the McGill University Health Center, the MUHC, for metabolic disorders and complication axis. In 2009, he became director of the Division of Geriatric Medicine's McGill University, as well as of the MUHC and the Jewish General Hospital. Dr. Moret is also co-director of the Quebec Network for Research on Aging and is lead of the Dementia Education Program for the McGill Faculty of Medicine and Health Sciences. He was founder and first director of the Center of Excellence on Aging and Chronic Disease for McGill from 2012 to 2015. During this time, he was co-leader for the implementation of the Quebec Provincial Alzheimer's Plan in primary care. He is also past president of the Canadian Geriatric Society. His research interest relates to the assessment of protein metabolism and cellular regulation at whole body and muscle levels, and of protein requirements with age, frailty, and diabetes. He is also participating in several studies involving the nutritional assessments of elderly persons with the aim of improving their nutritional status and level of physical function. He shares an interest in improving services and care to patients afflicted with chronic diseases. He holds research grants from the Canadian Institutes of Health Research and collaborates in several projects supported by provincial and national agencies. He has more than 150 publications, most of them in high-impact journals in the field of aging, nutrition, and metabolism. Before continuing, we would like to remind you to please mute your microphone on Zoom, and that if you have any questions, you could either wait until the end of the conference to ask them, or you could write them down in the chat box on Zoom. And now I'd like to invite Dr. Moret to begin his presentation.
Thank you, Caitlin, for this nice introduction. This is a proof that I've reached a certain age, otherwise you cannot accomplish so much at the beginning of a career. So this is the title of my presentation, What Muscle Has to Do with Brain. It's just one way of tackling muscle and brain. My mistake, if I put muscle with a capital M and not the brain with a capital B, must be a bias. Sorry for that. So I have some disclosures to make because I have given or received an honorary from Merck, Pfizer, and Astellas for different presentations. And we're going to tackle the topic of muscle and changes in body compositions with aging. And it is true for men as well as for women. And in this graph, what I'm representing here is that in general, at the bottom, if you look at muscle, that represents about 48% of our weight. As one increases in age, that percentage goes down to 25. And if most people maintain their weight, This implies that another compartment of the body has to go up, and this compartment is fat, because in young people, in young men, it's about 20%, and it goes up by 35% when you reach 75, 80. And for the rest of the body tissues, it's not a big change. But in summary, one can say that as one ages, there is a relatively loss of about 50% of muscle mass, and a relatively gain of about 84% of fat. The reason for that is fat is much lighter than muscle is, but this is what's happened as one ages. And it must have some impact in some of our functional capacity and performances as well. And I've dedicated a lot of research to understand that. Here is really what's happened in studies done cross-sectionally, meaning that we don't follow people for 4 years to see if their muscle is shrinking, but we compare young with old. And in this graph here, looking for muscle mass at the whole body level done through MRI, what we do see is that absolute amount of muscle goes down, as already alluded in the previous graph, and this starts to be noticeable at about age 45. There is an accentuation, an increase in the slope after age 70 or so. It becomes more abrupt, and this happens both in men and in women. And the result in terms of percentage is what I show you, that there is about a good 40% of decrease in muscle for men and women. And depending where you are, it can be more accentuated, increased in this particular study in men, because we start with the higher muscle mass, so there is more to lose. So the speed of that loss is greater in men, especially in lower extremities. And we don't lose it necessarily in a progressive way, because as life in general, there is events that takes place in our lives, and there is injuries and infections and diseases, activity, and there is a parallel between the losses that occurs and specific moments in life when we are put to bed to stay for longer periods. Inactivity is a major contributor to muscle loss, but there's also phenomena happening intrinsically in the muscle, in the body. An interesting observation is that in this particular study at the Baltimore longitudinal study, comparing again across age decades, is that the amount of muscle loss in white boxes here compared with loss of muscle strength in blue, one can see clearly that there is a greater amount of muscle strength loss than there is of muscle mass, with impact on daily functioning. And this is of interest to study. Though both are correlated, there is an increase of the white boxes as one ages with the blue, but the amount of blue, which is the strength, the decrease in strength is in fact 2 to 3 times greater than loss of muscle, let's say at age 80, 85. So there is an interest to understand both what is happening at the level of the muscle, as well in terms of muscle mass, as well as of strength. And the reason for that is across the lifespan, there is a minimum amount of muscle mass and strength, if you look at both together, that enables a person to remain autonomous, independent, capable of walking and doing its activities of daily living, and even capacity to enjoy life with more ease. And this is the threshold of disability. From childhood to midlife, there's a progressive increase in that strength and muscle mass, and then there is a decrease. But in certain individuals, that loss is so great that puts them below the threshold to remain autonomous. And thanks God, even if you are below this threshold, what appropriate rehabilitation, it is always feasible to bring it upwards so the person can remain autonomous and capable of function by herself. So sarcopenia, this is a complex complex graph here, but it's just to tell you that different organisms here is the foundation from the NIH or the European group on sarcopenia in older people. They advise not to search for sarcopenia unless it is clinically relevant. And reason for it is that you need special instruments to measure muscle. It cannot be measured just eyeball. For strength can be measured with less instrumentation, but if you submit everyone to DEXAs and MRIs, etc., our healthcare system cannot be maintained because of the expense of these tests and also accessibility. For this reason, we determine that the best way to proceed is measuring gait speed. This is the speed at which we move over, let's say, 10 meters or further in terms of distance. And if the average gait speed is less than 0.8 meters per second, then one should pursue more investigation to determine if there is a problem with muscle mass and strength using DEXA, etc. I won't dwell in this slide any longer, but for you to understand that the importance of all of this sarcopenia research, etc., is indeed to ensure that older persons remain capable, functional, and independent. So sarcopenia, by definition, sarcopenia is the loss of muscle mass and strength associated with aging. There is both intrinsic as well as extrinsic factors. So factors related to the body itself in its physiology, in its functioning, that with age leads to sarcopenia, as opposed to some lifestyle factors. And we're going to discuss this. Sarco is a Greek term for muscle, and penia is lack of. Same can be applied to bone. When we say osteopenia, means a weaker bone. And when it reaches a certain stage of weaknesses, then we call that osteoporosis. But the term penia is lack of, and sarcos stand for muscle. So as one ages, there are a lot of changes happening at our hormones, sex hormones, which is more obvious in women because they have menopause, but also in men, which is much more progressive, especially secretion of testosterone that has an implication in muscle mass. But there is phenomenon such as apoptosis, a scientific term that defines this regulation in our cells that gets rid of cells that are not performant. It's a process of cell destruction because they are no longer working appropriately, so that dysfunctional cell can be replaced by a new one that is functioning normally. But the apoptosis, as one ages, becomes less effective, leaving cells that are less capable continue their work, which contributes to the decrease in muscle mass and strength. There is also mitochondrial dysfunction. For those who don't know what is a mitochondrial, is that unit, that organelle inside of the cell that is responsible for the production of energy. You know, energy production is the ultimate function to sustain life, because we all need energy to live. And that energy is generated at the mitochondrial through the consumption of oxygen that we breathe through our lungs, combined with the food that we eat in terms of carbohydrates and fat. So it is at the mitochondria that we use what we eat with the oxygen that we breathe to produce energy. And there is a lot of research going on trying to define, is there mitochondrial dysfunction that could contribute to that decrease in strength? But obviously, your lifestyle, the choices that you do in life, has an impact in your health and your muscle as well. And we know that those who eat very poorly, for all kinds of reasons, as well as those who are very inactive, they lose more muscle than we do see with normal aging. And this, at least we can, act on it. We might not be able to act so much on the age-related factors, but those of lifestyle for sure. Other hormones that are of interest is growth hormone and insulin growth hormone factor 1, who also tends to decrease, but associated with physical activity as well. And then there is this notion of insulin resistance that I have done studies on it, because insulin is the most, I would say, anabolic hormone. So the hormone that contributes to growth. And this is done through eating. When you eat, your insulin is secreted and then helps to deposit the food you eat, your amino acids and fat and carbohydrates, into your cells to sustain your needs. But if you have insulin resistance, that function is impaired, and then this will inevitably contribute to more muscle loss. And here, the neurodegeneration, loss of motor neurons, is another important factor. And this might be the culprit to explain why there is more muscle strength loss than muscle mass per se with aging. Because if on top of muscle mass loss, you also have loss of motor neurons and motor units, then you're going to have a greater decrease in strength. At least is one hypothesis that a lot of people have been working on. We cannot escape the role of inflammation through some mediators of inflammation, here presented as IL-6 and TNF-alpha, because it's recognized that with age there is a certain amount of low-grade inflammation, and these hormones, cytokines, contribute to increase the amount of muscle degradation, muscle catabolism or breakdown. And obviously, if the amount of muscle loss is not replaced by new muscle, then you're going to be in deficit and contribute to sarcopenia. And once sarcopenia is installed, then there can lead to weaknesses and decreased metabolic reserves. What it means by metabolic reserves is that our muscle mass contains a lot of protein and nutrients that can serve for daily function. An example being that we need a good immune system to defend ourselves from infections. And if there is less amino acids, which are the building blocks of protein, there is less in the muscle, then our immune system cannot be as active as it should be. And there is a relationship between that muscle mass and the risk associated with infections. This is an example, could be trauma. If you have a trauma or a surgery, you need repair. You need repair to overcome your trauma, your surgery, or open up surgery, etc. And you have less proteins. It will take longer for you to recover. And obviously, all of this is a source of disability, morbidity, and mortality. Now, just to give you some background on muscle, this balance that I already mentioned about building muscle and degrading muscle. Muscle is relatively active in a sense that there is a continuous turnover. Turnover is a word to explain at any given time, there is a certain amount of new proteins being synthesized and a certain amount of proteins being degraded in the muscle and the whole body in general. And we need both. We need synthesis because when the food arrives, we have to deposit the proteins we take from, we have a fish or a meat meal contains protein. This protein, through digestion, is cut in small pieces, individual amino acids that we absorb. And using these amino acids, we synthesize our own proteins to remain ourselves. But at the same time, we need amino acids when we are not eating to provide for the different functions of the body. I mentioned already immune system, but could very well be for other functions of regulations and synthesis of hormones and proteins in circulation in the blood. So there has to be an equilibrium over 24 hours to maintain our muscle integrity. So that balance, we know that if there is more synthesis, as explained here with the bigger orange arrow, as opposed to degradation, then you will increase your muscle. And this happens through different mechanisms, but there is more synthesis than breakdown. And on the reverse side, if there is more breakdown in black arrow compared to orange for synthesis, then you have catabolism, you have shrinkage of your muscle. And nowadays, we understand the regulators of this phenomenon. On the synthesis side, we need food to provide us the amino acids coming from proteins to be deposited in the muscle. But for that to happen, we need, above all, the action of insulin to facilitate that synthesis. But in order to create muscle, we have to have mechanical stress. And this is what we call activity. The muscle needs to feel that there is, I would say, pressure on it so that it can generate more synthesis. And this explains why the bodybuilders, they are always in the gym pushing weights, because this is one mechanism to increase the muscle mass, but they need to eat a lot of protein. On the other side of the equation, which increases the breakdown, is lack of food intake, mainly protein and also energy in general from carbohydrates and fat. Certainly, the presence of high cytokines in circulation, following an infection or due to cancer. Cancer produces a lot of evil cytokines, these kind of hormones that has an impact on the body. This is why they lose a lot of weight, even if they are eating reasonably, okay? And inactivity, especially bad rest. If you're lying flat in bed for more than 12 hours, you start losing a tremendous amount of muscle. And this amount of muscle loss is higher in older people as opposed to young people, okay? It's why it's so important to maintain a certain degree of physical activity, mainly walking. You can run, but you're gonna derive, I would say, easily 2/3 of the benefit in muscle just by walking. If you run, you're gonna have extra, but walking is very salutary for the body as well as for the muscle maintenance. In this particular slide, I'm just illustrating to you the association that there is between the amount of protein intake and the loss of muscle as one ages. These results are taken from the ABC cohort in the United States that followed more than 2,000 patients over 3 years. Okay, they divided the population, the 2,000 individuals, according to their amount of protein intake. Quintile 1 means they were eating about 0.7 grams of protein per kilo of body weight. And quintile 5, they were eating 1.2 grams per kilo of body weight. 1.2 for a 70% kilo is about, I would say, 80 grams of protein per day. Think that and take the 3 onces. So how do you say, you know what I mean? About 100 grams of steak will give you about 50 grams of protein. So just to give you an idea of the amount people are eating in terms of protein per day and what's happened in terms of muscle loss over 3 years. What we do observe is in the quintile 5 eating 1.2 grams per kilo, they had nearly half of the amount of muscle loss compared with those who were eating very little, 0.7 grams per kilo per day. So one way to mitigate the loss of muscle as one ages is by eating enough protein in the amount of about 1.2 grams per kilo per day, which is in the range of 50 to 60 grams of protein, depending on your body size. I did studies on understanding these rates of protein synthesis, breakdown, what is the balance of the both combined. And I compared older men in light blue with young men in darker blue, as well as older women in pink versus young woman in darker pink here. In terms of protein flux or turnover, to show you that both men, older men and older women, had less protein turnover, which is the amount of protein changes in the body compared with their younger counterparts. When we look into the different components of this turnover or flux, we look into oxidation is one aspect of what we eat. When we eat, we burn a lot of food immediately. We call that oxidation for proteins. It was not at the oxidation level that there was significant changes observed with aging. When I measured the breakdown, again, there was no significant changes with aging in both older men and older women compared with their younger counterparts. The greatest significant change observed was in synthesis. Older men in light blue and older women in pink had less protein synthesis for the food they were eating compared with their younger counterparts. And this reflected in the balance over the period of the study. For sure, older men and older women had less balance. They were in a deficit compared with their younger counterparts. The good news is, in other studies that I have done, if I give a surfeit of protein to older persons, then they can compensate and reach the same amount of muscle protein synthesis as young people. I'm not producing these results here, but right now my intentions was to demonstrate that as one ages, there is a propensity to reach less balance in terms of protein synthesis and breakdown. And we have to be careful in the food we eat so that we can mitigate this propensity that comes with aging. I was trying in my presentation to make the link between the muscle and the brain, was the title of the presentation. And where this these two organs convey together is at the motor neuron in your spinal cord. This is where the muscle connects with the brain. Because in any movement one does, the intention comes from the brain, especially our frontal brain, that is transmitted into the spinal cord at the level of the motor neuron to then send an impulse, an electric impulse from a nerve fiber into a muscle fiber. And the motor neuron then reaches the muscle at this area here that we call neuromuscular junction. And it is then there is a release of calcium that contributes to contract the muscle fiber. And then as many fibers contract, then our muscle moves, and then we can execute the movement. What we do know is that this motor unit is the motor neuron that sends its fibers, axons, and innervates several fibers. And all the fibers that is associated with that motor neuron is called motor unit, okay? And what we know through investigation is that as one ages, there is a progressive decrease in the amount of motor units, okay? There is less motor neurons that innervates less fibers, which can generate less contraction, which will affect your strength. We have done studies in master athletes compared with those who are normal older persons. We compared about 10 men as controls versus 7 master athletes for men, and for females 6 control and 8 athletes. These athletes were master athletes participating in different international competitions, and consider all with reaching the 5th and above positions in the competitions. Like there is gold medalists, and there was bronze, but also we take up to the 5th position. So they're very performant. Their medium age was in the late 70s, beginning of the 80s. One can see that athletes are thinner, both in men as well as in women, compared with their controls for the same age group. They also have less fat mass, as you can see, implying that they are in fact having more muscle. And in terms of power, we did a specific dorsiflexion, the movement of bringing your foot up. And one can see, compared with their controls athletes, at a greater strength in their dorsiflexion of the feet, and showing that through a regular exercise, one can be much more performant than is with normal aging, let's say. And when we measure in these athletes and controls different electric potentials, we do see the skeletal muscle unit potential that there was a significant decrease in those who were controlled wait a second here, because master athletes. Okay, the negative peak amplitude, so is the reverse of the potential, was in fact the negative peak was lower in the athletes, or the reverse of that is that their action potentials were greater. And this is what you see here on the top graphic. Okay, and when we measure specifically in them the number of motor units at their tibialis anterior, which is the muscle of the lower leg, then one see more preservation of the motor units in these athletes compared with their age control people. So the one way of then mitigating some of the effect of aging is to remain physically active. We are not meant to be athletes, but the value of this information is to encourage one to remain physically active throughout life. And we derive a lot of benefit by walking. I insist on that because it's not everyone that can run. But obviously, if you are participating in some type of sports, being golf or being tennis, depending in the intensity, we are all doing something physical, including doing housework or gardening. Anything that is not in bed or seated in a chair, it's an activity that promotes good health and function. And in this particular study, where they were comparing 4 groups of people, young people as controls versus healthy older persons, non-sarcopenic, persons with a beginning of sarcopenic and those already with advanced sarcopenian state, one can see this top graph to the left, vastus lateralis. This is the major muscle of the thigh, and one can see that those who are non-sarcopenic, they have an average amount of cross-sectional area of the thigh similar to young people, as opposed to pre-sarcopenic and sarcopenic people who were much lower. When we measure in these people their motor neuron potential, one do observe that independent from being sarcopenic or not, there is decrease in the muscle action potentials, okay, unit potentials, as well as in the intramuscular motor unit number estimate. So there is something to do with aging in sarcopenic and non-sarcopenic persons. In this particular study, they did not verify the level of physical activity to explain some of these. But if you are not physically active, don't expect to have the same number of motor unit to being able to maintain your strength. And I will finish with this relationship between the muscle and the brain to tell you that the muscle is a very active tissue, in which, to this graph to the left, not only we take the glucose from the food and the fat that we take from the food to make energy, but also we produce a lot of cytokines that we call myokines, that has an impact in every single organ in the body. Okay, an example being you produce cytokines GLP-1 that contributes to absorb your glucose that will prevent diabetes. So having a certain level of physical activity, we can prevent this insulin resistance that eventually, if the resistance is very high, will lead to diabetes. This is an example, but it also has an influence or an effect on the brain. And one of the effect on the brain is to favor appetite. Okay, even though if you do a lot of exercise and you increase your IL-6, you might decrease appetite. Is the case, for example, when you are so physically active that you have aches and pains and you produce IL-6, it will affect your appetite. but there is many other hormones that will stimulate your appetite. At the same time, you produce through muscle BDNF, a hormone that contributes to hippocampal neurogenesis. In other terms, the preservation of your hippocampus necessary to maintain good memory. So everything is interrelated, so that physical activity then through increasing muscle activity produces effects at the level of the whole body, including the brain. I will take 5 more minutes to discuss mitochondrial function because it's of great interest to me. Here, mitochondria is presented as a cartoon and feeding your mitochondria, because mitochondria needs oxygen and needs substrate, carbohydrates from the food we eat or fat from the food we eat. So what's happened with aging, normal aging? I will finish with this chapter. So in order to understand the effect of aging and trying to separate aging from sedentarity, aging from inactivity, so we compared a group of young active men with a group of older active men. And active man is regardless of the age, they were engaged in moderate to vigorous physical activity comprising more than 150 minutes per week. And this is a long life trait. So we make sure that they didn't start exercising 2 years ago. These people were mid-70s, the older participants, but they were engaging in moderate to vigorous activity for the past 30 years in average, okay? This to say that we're trying to look at the effect of aging per se and not that combined with poor physical activity. One thing we observe as we are looking into their muscles, as depicted here by these pictures taken from the microscope, where we stain the fibers. The fibers in red are type 2. This is the fibers associated with development of strength. And in blue is type 1. These are fibers responsible for endurance, because we need different types of fibers to perform some work. We need a combination of strength and a combination of endurance so we can execute the task. This is why in runners, you have a greater number of type 1 fibers in blue, and in bodybuilders and those who do a lot of resistance, for example, those who do a quick run, the 100-meter champion, these guys, they are very built. Whereas those who do marathonians, marathons, they have much more number of blue fibers that enables them to do a lot of endurance exercise. So first thing to notice is, regardless of the type of the fibers, red or blue, the average diameter goes down. It is as if the fibers are not as it is, but indeed they are smaller in diameter. So our fibers, regardless of the type, is smaller in size. And this was well described. There was no difference in the types of fibers. NS stands non-significant. So for type 1, type 2, etc., there was exactly the same. So the distribution of the type of the fibers were the same, but the size of it was lower in older people. When you look into the mitochondrial function at the different steps of the electron transport chain, interesting enough, in these very active older men, they were able to produce the same amount of oxygen consumption. What I mean by that is they were consuming the same amount of oxygen to be used for energy, regardless of the age. Also, in the process of metabolizing energy, we produce reactive oxygen species, which is considered to be detrimental to health to a certain extent. But we did not find any difference in the production of ROS with aging in these very active physical men, older men. We measure also the calcium retention capacity, which is a measure of the earliest stage of failure of the mitochondria to work. And then we did realize that there was a difference at that level. It signifies that the mitochondria, for some reason, they were a bit less performant, okay? In terms of, they would be less healthy, quote unquote. And all of these measurements here has to do with that capacity of retaining calcium, because if there is a calcium leak from the mitochondria, means it is a less good mitochondria. So how does this less good type of mitochondria affects the mitochondrial function, knowing that they produce and they consume the same amount of oxygen? We look into more details of what is going on at the mitochondrial function to learn that there was a greater presence of endonuclease G, which is a marker of preparation for apoptosis. Again, that step in the cell or in the organelle, such as mitochondria, that has already been pointed out to be destroyed to allow new ones to replace that one that is non-functional. And even when we correct the mitochondria for its quantity in the cell, because you could say, you know, if there is less mitochondria, there will be also less endonuclease G. We did do these corrections, and we found that all of this is interrelated. The amount of parking per mitochondria was decreased. If we put all of this information together, what you realize is that preservation of mitochondrial respiration capacity and ROS production as shown to you. But there is an increased mitochondria-mediated apoptotic signaling because of endonuclease presence. But these mitochondria that are already prompted to be destroyed, they remain in place, meaning that the process through which, with age, we eliminate non or malfunctioning mitochondria is impaired, which can lead to a lot of less production of functional mitochondria associated with aging. So in summary, and I will stop here to allow questions, at the level of the muscle, from one side, we might have mitochondria that have some defects that have been not eliminated to allow new ones to replace and have very productive muscle energy production in one side. On the other side, there is decreased motor neurons and motor units, so that all of this contributes to the decrease in muscle mass and strength. I will stop here.